Welcome everybody. We're going to give everyone just a few more minutes to join our Water with Your Lunch webinar today. Thank you for being here with the Colorado River District. Welcome, thanks for joining. We're going to give it just another minute to let people come in here. Welcome everyone, thanks for joining. I don't know where you're coming from, but I look out our window and we are happy to see a little more snow on the ground. We'll be talking about that a lot today. Here the Front Range is exceptionally cold. Single digits and everything. All right, so we're going to go ahead and get started. Welcome to Water with Your Lunch here on the 22nd of February, Tuesday. We are excited to have you join us for the 12th installment of our Water with Your Lunch webinar series. We're looking forward to having all of the experts join us today to tell us a little bit about the health of the snowpack, to tell us what we can look forward to in the rivers this summer. And I encourage you all to ask questions as we go through these presentations. You'll notice that the chat feature has been turned off, so please submit any of those questions to the Q&A at the bottom, and we will be looking through those as they come in to share at the end of the short presentations that we're having. When you are joining us, if you have the option, please make sure that you're on mute and your video is off. Again, use the Q&A for any questions that you would like us to follow up on. In the chat, you'll also see help if you're having trouble joining us, or ways to reach out if you have any concerns about how the technology is working for you. So I'll go ahead and introduce myself. My name is Lindsay DeFreitas. I'm the PR and media specialist here at the Colorado River District. I joined this amazing organization in July. And Marielle Cowden, the director of PR, is on here as well, managing the back end for us. And Zane Kessler, our director of government relations, is also part of our external affairs team. Today, we're going to look at what the snow is doing, what it means for the rivers. But to get started, I'm going to give you just a brief history of the Colorado River District and our mission and our organization's current endeavors and all the things that we try to do day to day here. So first of all, the Colorado River District's mission is to lead in the protection, conservation, use, and development of the water resources of the Colorado River Basin. We're a government organization that represents the 15 counties of Colorado that you can see here on the slide. And these squiggly blue lines to the right represent the Continental Divide and the divide to the south down into a different river basin. You can see the main stem of the Colorado River, the Gunnison River, the Yampo and the White joining into the Green River briefly up there in the northwestern corner by Wyoming and Utah. So the Colorado River District represents the interests of the water users in all 15 of these counties. And we do that in a number of different ways. First of all, we try to keep water flowing to the farms and the ranches. We want it to flow west down to the Continental Divide and out the other side of the state, benefiting a lot of the local agricultural producers along the way, as well as securing legal protections for that water to keep flowing west, And this is what our Director of Government Relations is doing at the moment, very busy with the legislative session in Denver. We represent the legal interests of our water users. Maintaining healthy rivers goes along with this, and many of the partners that we are engaged with throughout the district work to make sure that the health and the vitality of our rivers continues. And then along with that, ensuring adequate drinking water supplies for municipal users in the communities across our Western Slope area. When we talk about our local river district communities, one of the other important parts that we're engaged with, one of our biggest projects, is the Community Funding Partnership, which was passed with ballot measure 7A back in 2020 with bipartisan support across our 15 county area. And it collects grants and awards them to different projects that benefit productive agriculture, conservation and efficiency, healthy rivers, watershed health and water quality, and also, of course, infrastructure, which has been one of the biggest headline items recently. So the Colorado River District Community Funding Partnership awards over $4 million annually for West Slope water projects. That's what we're doing now. The way that we got started was in 1937, when the local communities noticed in some headlines that Trans Mountain Diversions would be taking more water from the West Slope and diverting it to the growing population on the Front Range. So all of those users banded together to form this district so that we could speak up for the interests and the rights of water users here on the Western Slope. One of the reasons that you can see this is important has to do with this approximately 80-20 rule of conflict. So on the western side of the state, we have more than 80% of the water, which flows down from the headwaters of the Colorado River Basin, Yampa, White, Green, and Gunnison. And yet on the other side of the state, on the Front Range, we have growing communities and populations that represent more than 80% of the population. In fact, from the latest census data this past year, it's actually closer to 90%, 92% of the population on the Front Range. And those communities are growing very quickly. So the Colorado River District seeks to amplify the voices of West Slope water users so that everyone's needs are equally represented. And this continues to be in the spotlight as we look at continued population growth within our state. There's an estimated number of 9 million residents in Colorado by 2050. And the Colorado River Basin as a whole in the 7 states that it represents could be upwards of 70 million by 2060. So we're looking at managing a very limited resource with an ever-growing demand. Not only does that happen intra-state, but it happens interstate as well. From Colorado down, we have all of these interests and population areas that are looking to access the water that comes from the headwaters states. So we see the Front Range in gray there, and then we see all of those population centers in the lower basin that are needing to get the rivers that they've depended on, that they've built their communities around for agriculture and municipal use. And there's just a little bit less of that water, it seems, every year. And so one of the things that we're always trying to look ahead is to speak up for the river and for the needs of the communities, even as there's a little bit less of that water every year. With climate change upon us and the effects of a multi-decadal drought, we can see that for every 1 degree of Fahrenheit rise in temperature, stream flow can be reduced in the Colorado River Basin between 3 and 9%. And as much as we do love seeing the snow outside our window right now and more on the way, hopefully, we have to recognize that the state of Colorado is still across the board in some form of drought conditions. This map has changed a little bit. The yellows and the reds have shifted throughout the year, but they have been fairly consistent. And it's something that we need to keep in mind, and our experts will be covering that a lot more thoroughly than I will right now. But then just zooming out to see our whole region, it's not just Colorado that's struggling, it is the entire West. Our droughts have been persistent since the early 2000s. You can see that really quickly. Again, this is just a brief overview. I'm going to let them speak more to it. The natural flows, at least have changed quite a bit. So back in 1875, you can see on the left side there, the average flows moving up and down. And I want to draw your attention to the small yellow line on the right side, the one that sort of bisects that tall year we know is 2011. That's the 20-year average, and that actually does not in this map chart include last year's inflow. This is the Colorado River Basin's total flows as they enter by Lee's Ferry. It's dropped significantly. So we're looking at that orange line as the average from the last 100+ years, and then the yellow line as the average from the last 20 years. So that's one of the other things that we are constantly addressing is just there's less water in the river. What does that have to do with our snow? Of course, the Colorado River District, Colorado Snow District, but of course, the overwhelming majority of stream flow in the rivers of Colorado does come from snowmelt. So we call them the frozen reservoirs that are covering the mountains right now. It is the most essential storage that we have in the West because it allows the streams and rivers to fill throughout the season instead of depending entirely on rainfall. So it's sort of a delayed release. And that's why the health of the snowpack that we're going to dive into today is so important. It allows demands to be met even late in the summer. And when our communities depend on our local agricultural producers and recreation and industry economies, the health of the snow leading to the health of the river is one of the most important things for us to keep an eye on. So that's the brief introduction to our organization. You can visit our website, coloradoriverdistrict.org. You can follow us on any social media to see what it is we're doing from day to day. What I'm going to do now is take a minute to introduce our speakers for the rest of this panel. So first up, we're going to have, and I'm going to introduce all three of them, and then they're going to present different perspectives on the river and the snowpack from their varied areas of expertise. So first up, we're going to have Jeffrey Deems, who's the co-founder and chief technical officer at Airborne Snow Observatories. He helped pioneer the use of LiDAR snow depth mapping in support of hydrologic science, water management, and avalanche mitigation. He's a founding member of the Airborne Snow Observatory science team, and he has his interest and expertise in avalanche and snow hydrology research combine field data collection, modeling, and remote sensing in mid-latitude mountain locations in the Western US around the globe, and actively further connections between science and management applications. His website for his organization is airbornesnowobservatories.com if you have anything else you'd like to know about what he does. He'll be opening our discussion. After him, Paul Miller, who is a service coordination hydrologist with the Colorado River Basin Forecast Center, will be presenting. And he's been there for about 9 years. Prior to working there, he did work for the Bureau of Reclamation in the Boulder Canyon Operations Office for approximately 7 years, and he has a PhD in civil and environmental engineering from the University of Nevada, Las Vegas. And then finally, our third presenter is Dr. Sarah Tessendorf, project scientist with National Center for Atmospheric Research. And she received her master's and doctorate from CSU in atmospheric science and meteorology. She currently serves as the chair of the AMS Committee on Planned and Inadvertent Weather Modification and on the expert team on weather modification. Most recently in 2019, she was awarded the first UCAR President's Strategic Initiative Fund Scientific and Engineering Leadership Fellowship. And as a part of this, she developed a mentoring pilot program for staff that debuted and then designed a plan to expand the program for other staff across UCAR. So these three experts have a lot more to add than what I just gave you the very, very quick introduction. So I'm going to go ahead and turn it over to Jeff, and I'd love to hear what you have to say.
Great, thank you so much, Lindsay. Thanks everyone for joining during the lunch hour here. And like Lindsay mentioned, excited to see the flakes falling outside right now. I will give a brief overview of kind of where we stand with the snowpack so far this year, and talk about some new methods we're using to add to our existing arsenal of snow monitoring technologies. So it's been a bit of a roller coaster this year. We started out with some early snow, got everyone excited to ski back in October, and with the typical craziness on Berthoud Pass in October of people skiing dust on rocks. And then it kind of shut down for a while, and in early December, things weren't looking so hot. With headlines like "Grim Future for Western Water," and then all of a sudden, with a series of pretty powerful storms late in the year, all of the headlines switched to be ecstatic about how far above average we were. And then as the year progressed, it's been a bit dry for most of the Western Slope in January, to the point now where we've been starting to look at things and go, wow, is it going to snow again? And then this storm that's hitting us this week has got everyone fired up again for a massive snow dump. So it's felt like it's feast and famine in sequence this year. And here's what that looks like looking at the NRCS percent of normal maps, starting here on December 1st. Again, a little bit of early snow early on. These numbers, if you looked at these numbers back in October, they were vastly inflated with a very small amount of snow early in the season being a large percent of normal, just because percent of normal early is very little snow, or normal very early is very little snow. But here we go into December, and things aren't looking so hot. Folks were both from the water perspective and from the ski industry perspective, starting to get a little bit worried. And then all of a sudden, by the end of the year, this is January 1st, the Western Slope is looking like it's been going gangbusters with numbers exceeding 150% in many of these basins. Front Range and especially the Southeast weren't following along quite so rapidly, but still saw some good increases. And then going through January, not much happening on the Western Slope, although the Northern Front Range was pretty wet with a couple of northern storms that clipped the Northern Front Range, but missed most of the rest of the state. And here we are, mid to late February, and dropping down below 100% of normal for many of the basins across the state. Here's what that looks like in time series. This is the entire state of Colorado SWE time series from the SNOTEL network. And we could see pretty early on a slow increase, but well below the typical normal increase in snowpack. And then late in the year, big jumps up in snowfall and snow water equivalent. And then lately, over the past month and a half or so, slow increase with some small storms here and there, again, dominated by the Northern Front Range. But you'll notice that black line in January is a lot shallower in slope than the green line. So we can have slowly increasing water equivalent across the state, but dropping percents of normal. So we're not accumulating fast enough to be keeping pace with the slope of the normal accumulation. So that's why we've been seeing drops in percent of normal, even though if you look at individual SNOTEL sites or basins, you'll see slight increases over this time period. Another factor going on here is we switched normals this year. We moved the time period against which these percent of normal is calculated. Paul will talk a bit more about that during his presentation. So one question that we need to ask when looking at these filled basin maps is, are we getting the full picture? And one thing to keep in mind is that the percent of normal numbers based on the SNOTEL network and snow course measurements are used for runoff prediction. They are not a SWE volume, or snow water equivalent volume measure. And so they're used in the statistical forecasting method by the NRCS to project April through July runoff, but they don't give you a SWE volume. One thing to keep in mind is I changed the map here to show all of the stations, that these filled basins come from those station values. That we do not have snow water equivalent information covering the entire river basin. We only have it at a select set of stations. And so we rely on the relationship between these individual stations and the basins as a whole, compared to the period of record normals to allow a forecast. And that means that if we're in an unusual situation in terms of either the timing or the spatial distribution of snow water equivalent across these river basins, then that relationship with the period of record, and therefore a statistical forecast based on it, can become less reliable. Let's dig into that a little bit more. So this is a single snowtell site, the Copper Mountain Snowtell in the Blue River Basin, one of over 800 sites across the Western US. And this network really forms the backbone of snow monitoring across the Western US. This is an indispensable resource for tracking accurate time series of snow water equivalent at each one of these sites. And as most of you are probably aware, that silvery square down on the ground is the snow pillow. It's an antifreeze filled bladder that measures the weight of the snow that's sitting on it and reads out directly in inches of snow water equivalent. And as I mentioned, that this network was designed to support that statistical prediction of summer runoff by comparison to the 30-year normals. And this is the time series of just this particular snowtell site this year. Again, you can see the same pattern, general pattern of the state as a whole. Because we're looking at numbers that are based on this station network, how these stations are distributed across the landscape is important for interpreting these numbers. So this graph on the bottom left here shows the distribution of snowtell site elevations by each state in the Western US. I've got Colorado highlighted there, along with the lines top and bottom showing the maximum and minimum terrain elevations in each state. And you can see that there's quite a bit of terrain that's not sampled by this network. And so things can happen to the snowpack that exists in those areas that we don't detect by changes in the observed time series. Here's one way that can manifest itself. So here are two graphs from the NSIDC Snow Today page showing the snow-covered area in the Western United States for water year 2022, and then the right panel for just Colorado. And if you'll recall the time series map from the snowtell, we've been seeing slowly increasing snow water equivalent over the past month or so. And if you look at the Colorado map, we see that the snow-covered area, the area of the landscape that has snow on it, has seen some dramatic jumps. So it jumped up with this big storms late in 2021, and then dropped off, and then jumped again with some of the storms, especially the front range storms, happening in late January, early February. So if the snow-covered area is dropping, that's primarily due to decreases in snow-covered area, i.e. snow melt at lower elevations. So we're not seeing a decrease in snow water equivalent on our snow sensors. Additionally, and less detectable through this method, we see in dry periods sublimation losses from the snowpack. That's direct from ice, snow to water vapor, and loss of mass in the snowpack at the highest elevations. And the reason the snowtell sites are generally located in those middle elevations, but also in forest clearings. So they don't see a lot of wind. We don't see a lot of sublimation from those sites. And they're in an elevation belt that doesn't see a lot of midwinter melt. So they're not necessarily giving us the full basin perspective. And on unusual years, I think this is a good candidate for calling it an unusual year, with some really the roller coaster that we've been on with accumulation and dry periods. It is really a powerful perspective to see the entire basin snowpack rather than just that which is represented by the stations. So we really need this full basin perspective, I'll assert, to reliably assess our snowpack in this new abnormal that we're moving into. So here's that Copper Mountain context again. There's Copper Mountain Snowtell kind of center right. There's another one just over the ridge here at Hoosier Pass. And this is an Airborne Snow Observatory snow depth image from 2021 on April 18th. And you can see that there's a pretty dramatic variation in snow depth across the landscape. You can see where tree line is because this slow increase with elevation, you can see going from the blues to the yellows in the middle of the image, changes dramatically to a highly variable pattern of very shallow snow with some deeper pockets. And as we move into the melt season, later in the melt season, this is late May, that Copper Mountain Snowtell is now reading close to zero, if not nothing, or if not just a little bit, but you can see that there's quite a lot of snow left scattered around the landscape. So this is the motivation behind why we've developed ASO, or Airborne Snow Observatories. This project started 10 years ago at NASA Jet Propulsion Laboratory, and recently, a couple years ago, emerged from a technology transfer process from NASA to our new company, Airborne Snow Observatories Incorporated. We're doing the same thing we've done at NASA for 8 years, and with all of our same staff that jumped ship from NASA to join us. What we do is map snow water equivalent and snow albedo using a combination of remote sensing instruments on an aircraft. We use a scanning LiDAR to get snow depth, combine that with SNOTEL observed depths and snow water equivalent to give us densities and get us to snow water equivalent maps. Additionally, we fly an imaging spectrometer, which is a camera that sees in very fine spectral resolution bands from the visible wavelengths out into the near infrared and gives us a very high resolution picture of how much solar radiation the snowpack can absorb and therefore what its melt rate is. We couple these data streams with some physical modeling of the snowpack to allow continuous reporting on the state of the snowpack in each river basin. And we do all of this in a rapid turnaround process that we deliver data products within a few days of flying, such that the snowpack doesn't have that much time to change since we observed it, and these data can be maximally relevant for operations and decision support. So a couple more examples of what this looks like here. Again, is April 2021. This is down in the Animas River Basin. You can see Red Mountain Pass top left there, and Silverton is in this kind of snow-free valley upper center. And you can see Highway 550 making its way across Mullis Pass and Red Mountain Pass through there. And so some really interesting snow accumulation patterns looking to the north here in April. And as we move into May, we can see that snowpack melt out predominantly on the south-facing slopes. And we'll spin around here in a moment and look at the north-facing slopes. And not only can we see this snow accumulation and melt pattern across the landscape, we can the full basin perspective allows us to summarize it in unique ways. We can look at the distribution with aspect and elevation. In particular, the rightmost graph here shows the distribution of SWE with elevation for the two flights in April and May. And we can see that from the blue April trace going into the red May elevation trace, that we lost a lot of that low elevation snowpack. That's fairly readily observable, even to the naked eye standing on the ground. But as we look at the upper elevations, we can see that the snow water equivalent in the basin actually increased during that time period from mid-April to late May. And that's something that is not well captured, or not at all captured, by the station network, the SNOTEL stations being up to close to 11.5 in this region. So if you just look at the SNOTELs in this case, you're seeing that we've lost SWE during that time period, when in actuality we've gained quite a bit at the upper elevations. Another view of this same data set, this is looking up Overpass. Highway 550 is just off the, and Red Mountain Pass are just off the screen to the bottom. Here we are in April again. We can see all kinds of different snow accumulation and redistribution patterns in this image, from greater snow at higher elevations, and then lots of wind and avalanche redistribution of the snowpack. Moving into May, you can see again a lot of the melt out on the south-facing slopes, some evidence of a large wet slab avalanche cycle that moved a lot of snow to lower elevations during early May last year. And if we jump over the hill into the Dolores River, similar story there with strong melt between April and May. And I'll call your attention to the Black Mesa SNOTEL here in the bottom center. There's not a whole lot of change that goes on in that particular site. And so that makes that particular site a little bit difficult to interpret. It keeps snow late, which is great. It gives us data later into the season, but it's not showing necessarily a lot of the change that's going on in the rest of the basin. So these data also in part depend on SNOTEL observations for their reliability, but also lend context to interpreting any individual time series from SNOTEL or a set of them within a basin. And again, similar pattern to the Animus last year, where the upper elevations in the Dolores actually gained a little bit of snow, even though predominantly losing snow throughout the basin. So we're working to use these data in a decision support context. Here's a couple of examples from 2019, one in Dillon Reservoir, working with Denver Water to help them time their operations with Dillon Dam, showing them that there was still half of their snowmelt left above the SNOTEL sites in 2019. And they were able to delay their operations a couple of weeks in order to capture the second even larger snowmelt peak that happened in early July, and to do so without flooding Silverthorne. Successful operation when you could do that. And then also the Kings River in California in 2019, they had a similar high snowpack in 2019, and we were able to provide them some guidance suggesting that there was a good bit more snow in their watershed than they were ready for. They adjusted their operations to avoid a flood designation and meet all their water delivery objectives that year, which saved them from having to lease water on the open market in California, which would have come with quite a large price tag. So two of many examples now where we're seeing these data used in a decision support context, sometimes just the raw SWE totals for a basin, and all the way into putting these data into operational and research models. A couple examples of that. We're working with Paul and his crew at the River Forecast Center, Colorado Basin Forecast Center, to get these data into the Snow 17 SAC SMA model and explore ways that these data can be valuable in that context. On the right here, we're working with some folks at NCAR, Dave Gotches's group with Wharf Hydro, assimilating the ASO data into that model and using them to adjust or evaluating the adjustment on the ensemble streamflow prediction forecast methodology that they use. So looking ahead to, well, pretty much right now, Water Year 2022 activities in Colorado. We've got on the books 2 flights in the Blue River, the Fraser River, and the Upper Gunnison in the Easton Taylor in various stages of contracting. And then the Colorado ASO stakeholder group that I'll talk more about here in a moment has submitted a Colorado Water Plan grant to substantially leverage those existing plans and fund a few more flights in the Colorado Headwaters, South Platte, and the Dolores, as well as some snow-free data collection activities next summer to build out basins to be ASO ready for years in the future. Looking towards 2023 and beyond, there's a couple of different proposed pilot basins to add a substantial number of flights by the Colorado Airborne Snow Measurement Program. CWD-CB project funds will contribute next year as well. I'm still planning on where those will be applied. And then the Bureau of Reclamation has a new snow monitoring project or program that will be built out over the next 5 years and come to bear as well. So we have a stakeholder group in the state called, recently renamed to the Colorado Airborne Snow Measurement Program, or CASM. And their mission is to develop and communicate a roadmap for building out the Airborne Snow Observatory program statewide, and doing so in an equitable and sustainable way. So to date, we've put together, I'm part of this group, a report that should be coming out shortly, describing the needs and value of this program and laying out a vision for future implementation. And we've also applied for water plan grant funding, as I mentioned previously. This is a stakeholder group with well over 100 participants across the state and actually from neighboring states. And I encourage anyone who's not already involved to get involved. You can go to coloradoasoplan.org to learn some more. We have monthly stakeholder information calls and also a CWCB-led flight coordination committee that meets regularly during the melt season for information and planning of flights. So we're excited about the build out of this program and really not only supporting existing water management paradigms, but allowing a more flexible future with better snow knowledge going forward. So please check out our website at airbornesnowobservatories.com. Also the stakeholder group, coloradoasoplan.org. And in addition to any questions I can answer here, feel free to email me at the address there. And thanks very much.
Thank you, Jeff. That was very interesting. I have so many questions, but I will hold those until the end, till the Q&A. And again, just a reminder, if you think of questions, please put them in the Q&A as they come to your mind. And now I am going to turn the show over to Paul Miller with the Colorado Basin River Forecast Center to talk a little bit more about what he does.
Great, thanks, Lindsay. And let me share my screen here and put it in slideshow mode. Hopefully you guys can see everything now. But thanks again for inviting me to speak at your Water with Your Lunch webinar series. Had a good time last time, so I'm glad I get to come back. And I've tried to put a different spin on topics with regards to what we do at the Colorado Basin River Forecast Center. So I just wanted to give a quick overview of who we are at the CBRC and just really quickly scratch the surface of our popular products and services and how we're working towards improving those forecast products and services, specifically with our recalibration effort that we're very, very nearly complete and done, and then working with partners like Jeff, who just presented. So, just a quick takeaway, what our message is from this presentation, and then, you can eat or drink, however you happen to be spending your lunch period. But we do provide this really broad range of products and services for a really broad range of stakeholders. There's the super technical stakeholders like reclamation, like these water managers who use our water supply forecast and our short-term forecast to make literally billion-dollar decisions on the Colorado River Basin and its tributaries every day. But we also provide peak flow forecasts and weather summaries and recreational reports that are all available on our website. And we're constantly working to improve all this. So I encourage folks to go peruse our website. It's cbrc.noaa, so NOAA.gov. And if you can't find something, it doesn't mean it's not there. Sometimes we hide things a little bit on our website, not intentionally, but please feel free to email me, and I'd be happy to let you know where it is on our website, or maybe it's not on our website and I can work on getting you that data or working to provide you with the information that you're looking for. So at the CBRC, we're one of 13 RFCs nationwide, and we work with all 122 of the weather forecast offices. So when you get those warnings, those flash flood warnings on your phone, those are coming from our weather forecast offices, but we are providing reach back capabilities so that those offices can say, hey, how long is this flood going to happen? When do you think it's going to reach its peak? Do you see any downstream impacts that we should be concerned about? That all comes from our office. And so we're working really closely with the hydrologists at those weather forecast offices to make sure we're getting the best information out to emergency managers, the general public, whoever needs to know this information. In the West, because resources are so stressed and because Snowpack and Snowmelt are such big sources of water, Western RFCs have this additional role of providing water supply services to a lot of the big reservoirs in the Colorado River Basin and the other basins in the West. So we do provide these monthly water supply forecasts, and I'll show you a bit of an example coming up here. We do it at 174 locations throughout the basin. They're all kind of highlighted there on the left. We call them seasonal water supply forecasts because we're not telling you how much water you're going to see in a week. We typically are forecasting for the April through July period, though that period does change a little bit in the lower Colorado River Basin. We also do daily streamflow forecasts year-round at 460 locations, typically going out 10 days. And those are really important for recreationalists, for folks working to meet environmental flows for endangered fish or habitat restoration. And then, like I said, we work really closely with our weather forecast offices to issue those warnings, and they work very closely with the emergency managers throughout the US. This is a complicated slide, and I don't expect you to memorize this by any stretch of the imagination, but I really just wanted to show that we basically have two models working together that help us provide this information. And one's called the Sacramento Soil Moisture Accounting Model, and the other one's called Snow 17. And really, the most important part of this model is that we get the best information possible to drive these models. And like you just saw with Jeff, he's showing us some new data that we're really optimistic about, that can provide us with a lot of good information that we can use to feed these models. When I kind of click over here, we use lots of observed data, not just from folks like Jeff's shop, but also the USGS with their streamflow network, the Natural Resources Conservation Service with their SNOTEL network. We get constant information from the Bureau of Reclamation and other reservoir managers about how they're operating their reservoirs. And then we use weather models to use the best forecast information available. Again, we're talking with our resource managers to get their release schedules so that we're providing accurate forecasts. And then we come up with a lot of parameters that we infer through other means. So we don't use measured soil moisture, but we take a really hard look at the base flow conditions in the fall. We don't use measured evapotranspiration rates, but we come up with really solid coefficients to approximate evapotranspiration. And then we as forecasters take a look at this every single day, at least once a day, and come up with the best ways to make the model and incorporate all this information. And we do this even during telework. I kind of like this figure of the kids marching around the forecaster, because that's how it's been sometimes, but it tends to work out. This is what we typically look at on a day-to-day basis. So this isn't the pretty graph that goes out on our website, but me as a forecaster and all the really sharp people that are on our staff, we're looking, so this is for the Green River at Green River, Utah. And we're looking at forecasted temperature and precipitation at different elevation bands within that basin. You can see here on the left, I don't know if you can see my arrow as I'm kind of tracing it, but the blue line is our model, and the red dots are what we're actually seeing from the USGS. So you can see right here, our model is doing really, really well over the last 10 days or so. And because it's doing so well over the last 10 days, we feel really good with our forecast going out for another 10 days. And that's what becomes our official forecast that you can see on our website. So we spend a lot of time in the morning, every morning, and we kind of rotate through who's in charge of things each morning. This morning, just by coincidence, it happened to be me. So this morning, I spent a lot of time looking at all the data that was coming into our model. I looked at all our co-op stations, all the SNOTEL stations. I looked at all the streamflow information that we were coming in. And, I got a lot of help in the office too, but we just tried to get our model to be representing the past conditions as accurately as possible. And that sets what we call our initial state of the model. So we got our model as accurate as we possibly could for this morning. And from there, what we do is we use the next 7 days of forecasted precip and temperature data from our weather forecast offices. And then we cycle through historical precipitation and temperature traces to come up with those seasonal volumes that I was talking about earlier. So we start with 1991 currently, and we cycle all the way through 2020, and we come up with this whole range of volumes. And we put that on our website, and what that really looks like in practice is this. So we've so if you go and click on any of our of those water supply sites that I was talking about earlier, this blue shaded area is that range of possible futures, those possible hydrologic futures that we're seeing for April through July. And we start issuing these in January. And these pink lines are just our official forecasts that we issue at the beginning of the month. But more and more, we're relying on the raw guidance that comes out of our model. And so we update this plot every day through July. And you can kind of see this is from last year. And I just picked this one because I wanted to show you what the whole picture looks like once we get through things. If you go to our website right now and look at the current year, you'll just kind of see this left side of the plot that goes through most of February at this point. But this is how we explain risk and other aspects of our forecast to our reservoir operators. We tell them like the median forecast, which we used to call our most probable forecast, but it's really just the median of this forecast ensemble. That's this middle blue line here, and that's just the middle of all those 30 traces, all those possible hydrologic features coming through. And then this is the range. So maybe, a reservoir operator is trying to be a little bit more conservative, and they want to use a forecast that's a bit lower, maybe at the 70th percentile exceedance probability. Or maybe somebody's feeling pretty good, or maybe they don't have as tight a margin to work with as others do, and they want to use a forecast that's up at the 30% exceedance probability. But in either case, it gives those operators a chance to kind of evaluate the risk just based on what their operational goals are. So just and I'll just say, remember this plot because it comes into play on how we're evaluating some of the new data out there, like Jeff was showing. So like I said, we're constantly trying to improve our model. We're always trying to use the most up-to-date information. And what we recently did really over the last year and a half, almost 2 years, is we took the opportunity to update the normals in our model. And when we say that, basically we're shifting to the most current 30-year period that the World Meteorological Organization is using. And we do this to acknowledge the recent trends in climate data and precip and temperature information. And it's a really good opportunity for us to really evaluate our model. Do we have all the diversions right? Do we have all the reservoirs in there that we need to have in our model? And it also allows us a good chance to add new data and methods like what Jeff just showed us. So, a lot of these plots are just kind of showing different trends in climate change. So by updating to these new normals, it allows us to, one, take into account all the impacts from climate change and other weather trends, and also just take a really good look at our model and make sure that we're modeling things as accurately as we possibly can. So when we did this over this past year, kind of Lake Powell is the forecast point most folks are interested in. But when we updated from our old 30-year period, which used to be 1981 through 2010, to our new 30-year period, which is 1991 through 2020, we noticed about almost an 11% decrease in that April through July volume of streamflow at Lake Powell, which kind of aggregates all that flow up in the Upper Colorado River Basin. And then roughly the same over the course of the water year, which just goes to show just how important it is that April through July snowmelt runoff period is to the water year volume in our basin. Just kind of showing this in a more annual graphic flow. Our last official forecast at Lake Powell was on February 15th, and we're forecasting about 4.2 million acre feet over that April through July period. If you were using the 1981 through 2010 percent of average, that would have been 59% of average, that 4.2 million acre foot number. But now that we've updated to those new normals, 1991 through 2020 was a bit drier period than 81 through 2010. We're actually reporting it as 66% of average. So this is where, using percents of average or percents of median, you just have to be aware of what that reference period is. The value coming out of our model stays the same. It's primarily driven by the snowpack in the model. 4.2 million acre feet is the magnitude that we're forecasting, but how it's reported as a percent of average has changed a little bit. You can see just a little bit on these decadal averages. That 1981 through 1990 period was wetter than current conditions are. So, we're looking at about 12.8 million acre feet there. Since we've updated and incorporated this 2011 through 2020 information, just a little bit over 9 million acre feet there. So that's almost a 30% change in the volume there. And just over the last 5 years, it's even less, a couple 100,000 acre feet less than that. So just really indicative of the dry conditions that I know we have all been experiencing. So just to talk a little bit about how we're incorporating new information like Jeff's ASO information. Right now, when it comes to snowpack, we use this calibrated model that's been calibrated to gauge information from the SNOTEL network primarily. But what we're doing is we're trying to see how much better can we make our forecasts, including some of this airborne snow observatory information. So we're looking into substituting that ASO information instead of the snow water equivalent values into our model. And then we go ahead and we run that ensemble streamflow prediction system that I was talking about earlier. And right now we're just graphically comparing the forecast. We don't have the historical record to really make some statistical comparisons yet, but we're getting there. And so remember that plot I showed you before. So this is just a very provisional. We're just kind of using this internally right now. This just shows what our forecast would have been if we had incorporated ASO information compared to our official forecast. So this is that same exact site that I showed you earlier. The colors are a little bit different, but essentially this is the same plot. And you can kind of see in these light blue lines here, this is what our forecast would have been had we utilized the ASO information. And you can see it would have shifted our forecast down a bit. And you can see what the actual observed volume was in this dashed line where we ultimately ended up. And you can kind of argue that maybe we would have had a slightly better forecast a little bit earlier with the ASO information. But again, this is just for 1 year at one site. And we're just working with Jeff and other groups to get more of this historical information so we can really make some really good determinations. But we are cautiously optimistic that this is going to work out really well. And those are all the arrows that I had explained along the way. So we're doing lots more with other folks. We're working really closely with the Colorado River Climate and Hydrology Work Group to do lots and lots of different research projects, all aimed at improving our forecast. We're partnering with several universities and researchers to investigate potential improvements in other ways, not all of them snow related. And we work with the Bureau of Reclamation and other agencies on funded research efforts. There's a bunch with the Bureau of Reclamation, and just recently we've been working with the USGS on a couple other funded research efforts. So yeah, lots of work to be done. There's no shortage of stuff to do. So yeah, if you have any questions, please feel free to reach out. My email address is really easy. It's just paul.miller@noaa.gov. And yeah, would love to talk about this more if anything was particularly interesting to anybody. Thanks.
Thanks, Paul. I really appreciate that. Some very interesting overlay between what you and Jeff are doing, and a lot to look forward to in the future, hopefully. And taking us in that direction into future looking. Up next, we have Sarah Tessendorf to talk a little bit about her area of expertise and what she's doing with weather modification and how it impacts this whole conversation. Sarah?
Hello, thank you. Yeah, my name's Sarah Tessendorf. I'm a project scientist at NCAR, and I do a lot of work on cloud physics for the last 15 years. And one of those areas is on cloud seeding research. I'm leading the weather modification research group in the Research Applications Lab at NCAR. So I'm going to talk about our recent advances in this field of research. But first, let me start off by introducing you to the topic of cloud seeding, if you're not familiar. It is most often performed with the goal of enhancing precipitation. And this type of cloud seeding that I'm going to talk about today is winter orographic cloud seeding, which focuses on targeting wintertime storms in the mountains. The goal of this type of cloud seeding is usually to increase snowpack, those reservoirs in the mountains that Lindsay mentioned earlier. And sometimes it's just for the snowpack, like if you're a ski resort, but most of the time it's also the ultimate goal is for enhancing that subsequent stream flow from the snowpack. The conceptual model for this type of cloud seeding is outlined on the slide here, and you need a cloud. That's the basic criteria. You need a cloud that contains supercooled liquid water. So water does not always readily freeze right when it gets to the freezing point of 0 degrees Celsius. It can remain in a liquid state at temperatures colder than that. And when it's in that state, it's a sign that the cloud is not efficiently forming precipitation, especially snow, ice-based precipitation, as efficiently as it could. It also poses a hazard to aircraft that fly through those clouds because the liquid water can readily freeze on the sub-freezing airframe. But so what the goal is here is to introduce ice nucleating particles into the cloud, typically in the form of silver iodide that has been shown to nucleate ice at relatively warm sub-freezing temperatures compared to naturally occurring particles, ice nucleating particles in the air. And the silver iodide then can be released either through an aircraft directly in the cloud or above the cloud, or from a ground-based generator where then that plume of silver iodide needs to disperse up and into the cloud. Then once you get that silver iodide into the cloud, it can nucleate the ice crystals if it's at the temperatures colder than about -5 or 6 degrees Celsius is when that will start to nucleate. And once you get ice forming in these clouds, it can then readily form snow through ice-based precipitation formation processes at the expense of that supercooled liquid water. So it's like wringing out that supercooled liquid water into the form of snow. So that's the overall concept here, and it's been around for decades, but the challenge is once you seed a cloud, you really don't know necessarily what would have happened otherwise. So it's been really hard to evaluate and quantify the impact of cloud seeding over the years. But we've made some advances recently in the science. Let me see if I can get it to advance forward. There we go. We've made some advances in 2 key areas recently in the last decade or so that have really moved things forward. And one of those is the development of what we call the WRF weather model. This is a model that simulates the physical effects of cloud seeding with silver iodide. Now, this was made possible in part by the recent advancements in supercomputing. The fact that we have supercomputers that can simulate really high resolution, run really high resolution models and more sophisticated models has really allowed us to change the game when it comes to modeling the weather. And so this has been one key component. The other is the collection of groundbreaking observations that we collected in a recent field campaign called Snowy that I'll talk a little bit more about today. These observations coupled with the WRF weather model are really transforming the way that we're designing and evaluating cloud seeding programs. One of the first breakthroughs that our group did about 10 years ago was document that you can now realistically represent precipitation in the mountains with really high resolution model simulations. Again, this is that supercomputing came along and really advanced. And so we said, let's run these larger regional scale domain model simulations at grid spacing down to 2 kilometers. A lot of our previous models would be as coarse as 36 kilometers, especially if you're doing a really global or larger regional scale model. And so this is an example from the Colorado headwaters region where you can see when you simulate these multi-year long-term simulations of precipitation with a grid spacing of 36 kilometers versus 2 kilometers, the picture looks quite different. In fact, if you look in the northern headwaters region, you could see that, the precipitation might have been simulated to be only of about 350 millimeters, whereas at the 2 kilometer grid spacing, you can get well over 1,000. Compared to the SNOTEL observations, which are shown as these dots here, in this panel, you can see that the model is now getting the magnitudes of precipitation accumulation over the year much more in line with what the measurement sites show. But also tying this back a little bit to Jeff's presentation, you can see the limitations of site-based measurements like the SNOTEL network compared to having spatially resolved measurements like the ASO provides or like these high-resolution models provide. But this was a real groundbreaking component to show us that the models are now sophisticated enough, and if we run high enough resolution, we can get a pretty good representation of the precipitation. So now let's introduce another sophistication to the model. So this is an animation that illustrates how WRF weather mod works. This is an animation over a very small domain with 2 mountain ranges. You can see the white areas are the areas of cloud with supercooled liquid water that have formed over these mountain ranges. And then the silver iodide particles are being inserted into the model at an altitude where an aircraft might fly as the cyan particle plume here. Once that silver iodide reaches the supercooled liquid cloud, you'll see some yellow form. It'll restart in a second. That embedded yellow is the ice forming from the nucleation of the silver iodide, and then the snow forms below it in the green. Now you see plenty of other regions in this simulation too, where the green representing snow is occurring because of course the model is still simulating naturally produced snow. But once we run these simulations now with the physical effects of silver iodide seeding in them, we can compare a simulation with seeding to a simulation without seeding and look at the differences. And so that not only allows us to quantify the impact, but spatially map out the impact as well. So that's one major advance. The other advance is in our observations and how we've measured the impacts of cloud seeding with observations. And one of the reasons we set to the field for this campaign called SNOWY, which is an acronym that stands for Seeded and Natural Orographic Wintertime Clouds, the Idaho Experiment, which was funded both by the National Science Foundation and Idaho Power Company. We, of course, want to better understand the physical effects of cloud seeding. So we sought to get measurements in the clouds that were being seeded in order to physically measure those impacts. But we also were at this point really interested in getting some very important measurements to validate and improve the WRF weather mod model. Because once we develop this model, we can compare it with some measurements of, say, precipitation gauges and so forth that allow us to know that the precipitation is being formed well. But we wanted to make sure that the physics, all the cloud physics steps that I showed on that initial conceptual model diagram, we wanted to make sure the model was getting all of those other steps right. And so we went into the field with a research aircraft from the University of Wyoming. We went in with an aircraft that had seeding flares on it so that we were seeding with aircraft as well. We had 2 Doppler on wheels radars up on the mountains to give us radar measurements in places where the normal National Weather Service radar network doesn't actually get good observations because the mountains themselves block the measurements. And then we, of course, had a suite of other ground-based measurements, snow gauges, we did weather balloons, we had microwave radiometers and so forth. So one of the key goals here was to try to fly the research aircraft directly in the silver iodide seeding plumes to detect and measure those impacts of seeding. We wanted to quantify how much ice is being produced, for example, from the seeding in these clouds. So the goal was to fly the seeding aircraft in a way that would be perpendicular to the wind. So with this cartoon here, you can see the wind from the west. The seeding aircraft track is the red line flying back and forth, north and south. As it's releasing silver iodide, it will disperse downwind and form this zigzag-like pattern of dispersion. And then we would fly the Wyoming King Air research aircraft along the wind to sample in and out of that plume of silver iodide. And the goal to then detect those enhancements in ice concentration that would be due to seeding. The vertical cross section of this is shown here on the right as well. So a key highlight from SNOWY, if you haven't seen this before, is that we were very successful in doing this. In fact, here's an example from one of our key cases where this is the Doppler on wheels radar domain that I'm showing you here in the middle. The winds on this case were out of the southwest, so the seeding aircraft track is shown in yellow, and the aircraft location is actually the orange dot. So you can follow it back and forth if you want, but I'm going to draw your eye to the radar reflectivity itself, which at this time, at the beginning of this case, there was not much radar reflectivity seen in this case. So we were seeding, and then lo and behold, we started to see a zigzag pattern show up on the radar. And then we stopped seeding, and not long later, it went away. I'm going to go back and stop it on a few of these times here where you can very clearly see that zigzag pattern. When the aircraft is seeding, it burns. There's two types of ways it burns flares of silver iodide. It can burn them continuously through the flares on the back of the wings, and that's what you'll see give us this more continuous line of zigzag. It can also release them through ejectable flares below the aircraft every 30 seconds. And in one of the flight legs, they did just that. They only did ejectable seeding in this case, and you can see that dotted line pattern there from the release of the silver iodide from those distinct ejectable releases. So this was a really key case because it documented, one, we observed this zigzag. It was unambiguous pattern. Nature does not produce zigzag-like patterns. We actually collected this type of data in 3 cases where we have these unambiguous zigzag lines. But more than that, we collected radar data and in situ measurements in these seeded plumes as well. And so that was a huge breakthrough for the Snowy campaign. It really helped us achieve one of our key goals so that we can use these data to better understand the impacts and quantify the impacts of cloud seeding. So that's one of these key recent advances. And we have these new opportunities for studying the physical effects of cloud seeding using the Snowy data. We also, though, can use those data to validate the WRF weather model as we had hoped. We have those in situ measurements in the seeded plumes where we can compare directly with the model simulations to make sure that the model is producing the right amount of ice from the silver iodide and so forth. We're also finding that the WRF weather mod and high resolution WRF modeling framework can be used to determine when, where, and how to seed. So we're able to use the model now in a guidance kind of scenario, as well as for designing new programs. And the ultimate goal for a lot of this research is to try to quantify that impact of cloud seeding in a cost-effective way too. A lot of traditional methods using statistics, especially randomized statistics, take years and years and years to get a sample of cases large enough to run the statistics. And that can be very costly to run these experiments for years and years and years just to try to understand what the effect is. With a model-based approach with WRF Weather Mod, you can get this, you can analyze it on a case-by-case or a year-by-year basis. You don't need to run and get a large enough sample like you do for statistics. So it can be a cost-effective approach in that way. In addition, because we can spatially map out the simulated seeding effects, we can couple these model results to things like WRF hydro, the hydrological model that Jeff mentioned earlier, that then we can drive a spatially distributed hydrologic model like WRF hydro to simulate the streamflow impacts of cloud seeding as well. And so really, we've got a lot of new opportunities now from in the research, in our ability to design and guide cloud seeding programs and to evaluate cloud seeding programs that really make being in this field of science a pretty exciting time right now. So I'll just wrap up so we still have some time for questions and just reiterate that, you know, our Snowy Field campaign collected an unprecedented data set for studying cloud seeding. Modeling capabilities have advanced, especially in the last decade. We now feel very confident that we're realistically representing precipitation and atmospheric conditions in the mountains based on these high resolution model simulations that we've compared with observations to show that. And all of this together now has led to the development of a model that can simulate the effects of cloud seeding, which we call WRF Weather Mod. And we use this model to design new cloud seeding programs, to guide real-time operations, and to evaluate the impacts of cloud seeding, both on the precipitation and when coupled with WRF hydro, can also simulate the impacts on streamflow. I also have my email up if anybody has other questions beyond the time that we have today. And I also want to acknowledge many folks that I work with at NCAR that have contributed to this research and development over the years as well.
Thank you, Sarah. That was really informative and helpful. Some very exciting cutting edge stuff going on there. We are running up close against the time here at the end of our webinar, but we had just a couple questions I was going to toss out very quickly. We've got about 5 minutes. So Paul, I have one for you. We wanted to ask about the 30-year average. It's been updated, bumped up a decade. And the question is, why is it 30-year static and not a running average that you all use in that instance?
You know, that's a really good question. I think mostly it's just based off of the world meteorologic standards that are adopted worldwide, and just the Weather Service trying to stay with those. I will say, as an RFC, as the Colorado Basin River Forecast Center, we do things a little bit different than some of the other river forecast centers. For instance, the California Nevada River Forecast Center, every year they tack on that new year, and so they're always using that 30-year average as a reference period, but their ensemble keeps growing and growing and growing. We run our model to run through the 1981 through 1990 years. So those are available if people want to look at it, but we just kind of develop our forecast from that 30-year period. So all the RFCs are a little bit different.
Very interesting. Thank you. Jeff, I have a question for you. You mentioned that in your presentation that we don't get the full picture often with SNOTEL sites, and we discussed why they're so point dependent. And I was just wondering, in the state of Colorado, is there a basin that you feel like particularly suffers from this limited data set? Or is it sort of equally spread and impactful in all different river basins?
That's a good question. You know, often the Arkansas has jumped out to me as having what looks to be less SNOTEL coverage than others. It's got a number of fairly unique snowpack environments within it, and I'm not sure that the limited number of stations currently captures all of those. That's sort of off the cuff. I don't have any actual data to back that up, but that's always leapt out at me from the map. A lot of times, kind of relevant to that question, a lot of times stations that are in adjacent basins get included in averaging for a particular basin. And I'll call out the Colorado Basin River Forecast Center has a snow data page where you can actually pull data from the NRCS and plot different stations together. And there's a whole bunch of different snow groups, SNOTEL groupings on that page that folks often use to aggregate SNOTEL data in different ways. And that can be a really powerful resource if you know, for example, like in the Upper Gunnison, the Schofield Pass SNOTEL site is often used to evaluate the snow water content in the East River. It's actually in the Crystal River headwaters. It's not literally within the basin, but it is seen by many to be a good representation of part of that basin. So there's no one way to interpret SNOTEL data. So tools like that, I think, are really useful to exploring different ways to do so.
Thank you. I know I'm squeezing this in here. I'll get my wrap up, I promise. But Sarah, I had one question for you. We talked a little bit about the feast and famine cycle that we've been in, sort of this weather whiplash that we've seen this 20 or 22. Do you see these large storm events spaced out in drier periods as an opportunity when we see like such an extreme storm event as December? Or would cloud seeding, do you believe, or from your modeling, have you seen be more effective with continual small cycle storms?
Yeah, that's a good question. Cloud seeding really is going to have the biggest effect in storms that aren't efficiently producing snow on their own. Now, that's not to say they're not producing any snow, but the storms that have the most supercooled liquid water in them. And so I think generally those are going to be storms that might be a little bit more of your moderate to maybe lower snowfall producers naturally. But that's not necessarily the case, because it's all really a balance of how much moisture is coming into the storm versus how much snow is being produced. And if you get a storm that's got a really strong moisture supply, you might still have quite a bit of supercooled liquid water in the cloud too. So, but either way, I do always suggest, cloud seeding is a tool not to bust a drought. It's a tool to maybe try to augment a little bit throughout. And so it's certainly not going to be as effective typically in your drier years where you just don't have as many storms in general, because it definitely needs to be used consistently.
For sure. Well, thank you all so much for being here. We are out of time. Folks, they've generously offered you emails if you have other questions that you would like to ask to follow up on, and a recording of this webinar will be available on our YouTube channel in the next few days. And if you registered for the event, you will get that in your inbox as well. So thank you very much for our panelists, participants, and everyone who came to join us today with this Water with Your Lunch. I hope you have a nice Tuesday. Thank you. Thanks.